morning, everybody. I am Krishna Kumar from Krishna's classroom. We begin with another lecture on quotient spaces. Before that, this is the first recording in the new year. We have left behind a very chaotic and challenging year, and is now looking forward to wonderful days. Let me wish you all that 2021 would be something where you want to achieve everything you have in mind. Well, let me just start with the abstract formulation of the quotient spaces. What we have looked at in the last two lectures were the geometric picture of what are called quotient spaces. Now, so let us follow the path that we have tread in those two examples. So we start with a vector space V. Let V be a dimension over a field so it's essentially a finite dimensional vector space that we are working in. Let M be proper subspace of V with dimension of M. This inequality ensures that the subspace M that we have picked up is a proper subspace. Now we start construction as we did in the case of R2 and R3. Let me put on this side a picture of R2 to keep track of things. That can be interesting. So this is R2 over R with M, a one-dimensional subspace, which is manifesting itself as a line passing through the origin. Now we start working on the sets. Consider the collection. X plus M. All elements of the form X plus M, X belonging to okay, which is essentially, and recall, this is the collection. So these are subsets of V, but subsets with a very nice structure. So let us see what is going on in the one-dimensional space. We have a particular x that you pick up. Now you see that if you take x plus m, this is actually x plus y. So you choose some y here. Suppose this is y. Then you are completing the parallelogram when you take the sum. And what you end up with would be simply the line, a line parallel to it. So you have, if you run y over m, then this point also would start running over a line parallel to it, because it's a parallelogram law of addition that we use. We already seen this. So you end up with this line, but you don't reach anywhere else. Okay? But there is also a thing that we have observed, that if you were to use an x prime, which lies on this line, then you see that x prime plus, this is x plus m, and this is also equal to x prime plus m. So for any x prime lying on this, you see that x prime plus m is equal to x plus. And can you really characterize it? This is what we have observed, that the relation between x and x prime is that x minus x prime, this is x minus x prime, x minus x prime lies on n. In fact, this is a necessary and sufficient condition. So we write, first of all, observe that x plus m is equal to x prime plus m if and only if x minus well, it needs a proof, and it's not difficult to prove this, because x plus m, take a typical element of this, then that is equal to a typical element of this, which means this relation is true. Then you see that x plus y1 equal to x prime plus y2. Okay. So x minus x prime is y1 minus y2, and y1 minus y2, both y1 and y2 is in M, and M is a subspace. Therefore, y1 minus y2 belongs to, or y2, I think it is, y2 minus, this is x1, x plus y1 equal to x plus y2. So x minus x prime, y2 minus y1, and y2 minus y1 is in M, which implies x minus x prime is in. Conversely, suppose x minus x prime is in M, then you start with an element here. It is of the form x plus y, and x minus x prime is in M means that x is equal to, so x minus x prime belongs to M implies x equal to, let's wait for some weight. So if you substitute in this, you get x prime x plus y1 x plus y equal to x prime plus y plus y. So this is essentially an element in M, therefore this belongs to x prime plus. So one can easily verify that this is true. So this is another solution. And you see that gives us a classification of vectors in V into equivalence classes. So note that x related to x prime defined by the space with an equivalence relation. Again, let's prove it. We have already done it in the other case, in the case of examples. This is an equivalence relation. So what it does, it partitions V. Classes which are disjoint and the union of union giving okay. So that's it. So in R2, this amounts to all lines parallel to the given line generated by various vectors. So what you have is this. If you denote by bracket x n, then we have bracket of x bracket x prime if and only if this is the relation that we have. So the collection of, we have now a new set and each one is called a quotient. So what you have is that V is essentially equal to union x belonging to V of, and you see that x intersection x prime is equal to is empty x is not related to x prime in the sense in which we have defined it earlier. This is the one. This is not related to x prime. But if x is related to x prime, then x is equal to the bracket x is equal to the bracket x prime. So we denote by b by m the quotient series of b with respect to m as the collection of all x. Okay, right. So we have constructed a new set. The new set consists of all these lines parallel to M, or what we call the translates of the subspace M to X. And you see that this forms a disjoint union. Right. Now let me go further and then try to do some kind of algebra on that. So we take E by M. Define does it make any sense? That is that mod x is this sensible? The question is relevant because you know that x can be obtained or maybe let me use y then. This question is relevant because you have x generated not only by x, with bracket x generated not only by x, but by any other x prime which has the property that x is related to x prime. Okay? So, your definition here is based on the sum of x and y. But what if someone else writes x as the bracket x as x prime? Okay. Suppose and y prime, it's quite clear what they are. Okay, that means we are assuming that is x minus x prime belongs to M. And then what do you have? Then you see that x plus y is also equal to x prime plus y prime, which is equal to x prime plus y prime by what we have. But to substantiate or justify this as a definition, we have to show that these are the same. That's important. So what we prove is that irrespective of what representation you choose, you add up, you end up with the same quotient. That's what has happened here. If you take x here, then say y here, suppose this is y, then you take x plus y is by adding these two vectors to the parallel, therefore this is x plus y. And then what it makes is a line. So this is your line x plus y. Is this also equal to x prime plus y prime? Let us investigate. That means I am choosing a y prime. Say I am choosing a y prime lying on this line, the same line. So I have x prime minus y prime is a vector in M. Okay? Oh, sorry. What did I say? Yeah. So what I need to say is that y minus y prime is a vector in M. So also x minus x prime is a vector in M. This is what you have. Now the question I am asking is, suppose I add x prime to y prime, what do I get? Do I end up on this line? That's the question that you ask. So what do? You start adding them. If you add them, this is what's here. And you see that the line, the parallelogram law will give you the addition here, and this line is essentially the same as the other one. I it out in the graph to enjoy doing it, or even analytically prove it in R1. Okay. So what you observe is that if how do you prove that? See, you have to check this. They are the same provided x prime x plus y minus x prime plus y prime. This is equal to x minus x prime plus y minus y prime. And this this belongs to M. Because x minus x prime belongs to M by our assumption, y minus y prime belongs to M. Therefore, this implies so what have we proved? We have proved that irrespective of what representation you use to describe x plus M and y plus M, x plus y plus M sum that you get is the same quotient x plus y plus m. That's what we have proved. Okay. Therefore, addition is well defined. Hence, we shall take define x the definition is well defined. There is no ambiguity at all on the choice of the representing vectors. What happens to the scalar multiplication? Does it also follow the same sort of thing? That is, we start with an x. Start with an x. Now, what about alpha x? See, alpha x or cx or a c, suppose this is x and this is cx, then this line is what you call okay. Now you choose an x prime. Choose an x prime here, and then choose what is called, then you see that this is cx prime. That's something which you have to geometrically prove. Okay, that cx and cx prime lies on the same line parallel to m. I think we have done that. And it would be very nice working it out with the representation of m given in the vector form and then completely using vector form all along, or assuming x plus m is in the usual analytic form, namely m is given by a1 x1 plus a2 x2 equal to 0, and then working out all these in the analytic form. It's a good exercise. So I give it as an exercise. But before that, let me complete this. Okay. So how do you prove this? So the next part is we propose Cx is it well defined? Again, you see that if x prime or x is equal to y, then so let us work out. So Cx this is the set Cx plus m. Now you see that an x plus z Okay. This way. Our claim is that Cx plus M first of all Cx is equal to C times. How does it come? It's easy that Cx plus Z equal to or C naught equal to 0. But Z belongs to, so this is equal to C into if Z belongs to M, Z belongs to M implies C by Z by C belongs to M whenever C is not equal to 0. Otherwise, it's quite simple. It is Cx. If C is 0, then there is no question because what happened between 0 plus M, you are in M. Therefore, you see that this is well defined. Therefore, you can conclude that Cx plus M equal to C times x plus. That's it. Therefore, that is there. Now, is it well defined? Is it well defined in the sense that we use different representations? As the result hold. Suppose so you see that you write Cx minus Cx minus Cy C into x minus y, and if x minus y belongs to M implies therefore it follows that the cosec Cx is equal to the cosec. So that is done. Okay. Therefore, you see that hence scalar multiplication is well. Now, what you can verify is that the V by M is A. V by M is a linear space over. What are things you need? I'm not going to do proof of that. You can show that, easily check that it is associative. Addition is, it is associative with respect to addition. It's commutative with respect to addition. Then M serves as identity element which means that is M is equal to some X or Z where this collection. Sorry. Okay. And what you have to prove is this, that X plus it is enough to prove this, that see X plus and suppose then okay, therefore you get therefore this is or in the other notation if you have X plus N plus N which is also equal to therefore the zero element of the quotient space is M. Or in other words, the given line or given subspace passing through the origin serves as the zero element. Okay, and you can easily check that if you take an X and take an element on this line and then add, you end up with a point on X plus. So that's all easily verified. Further, you have zero independent vector space. This is essentially. Therefore, for X plus M, you have minus X plus M as the inverse. Now I leave it to you to verify all the other things like distributive property, like C verify. Cx plus y. Now c plus dx equal to and then you have 1 into x then what form? Zero. That means 0 into x plus m will give you m, because it is 0 times x plus m. That's all easy to verify, and I think I can done more or less all of these. Okay, fine. So these axioms of the vector space are satisfied by this class of quotients. Hence, it's a vector space. It's a vector space which has been generated from vectors in V and the subspace M. Okay. So this is called the quotient space. Which is a vector space. Obviously, one of the questions that immediately come up is, can you say something about the dimension of what can you say? The dimension of well, it's clear, or it is just common sense to believe that it's going to depend on n and m. Okay, sensible to expect depend on both. Then the question that you ask is, what is the I gave an indication to this relation last time towards the end of the lecture. Okay, that it is likely to be n minus 10. And that's a worthwhile speculation that we easily make. And if you want to be sure about it, you can go to the example and have a look at this. Okay, right? So what you end up here is that if you take two parallel lines and add them up, you end up with another parallel. You take a line parallel to M and then multiply by a scalar, you end up with another line parallel to M. And then of course we have already defined a well-defined addition and scalar multiplication made it equal vectors. Now you are asking what is the dimension of this space. Now one thing that you observe from your example is that if you take a vector, see this is the subspace that we started. So you start with a vector which is not in this subspace. Okay. So I start with a vector which is not in the subspace. So let me just draw this. This is a vector I start with, not in the subspace. The X. Now you look at the collection Cx, or the line generated by the vector X. Sorry, the line generated by the vector that I have chosen. Okay, well. Now, one observes that every point on this line intersects a line parallel to the given subspace exactly at one point. Okay. Therefore, every one of those elements do generate the elements of V by M. And what is the implication? You can add two such elements, say X and Y lying on this line, and if you add them, you end up with another line on this. Or if you take a scalar multiple of the particular X that generates this line, then it is going to be another point on the same line. Okay, and you see that every point on this line generates a quotient, and you see that corresponding to two vectors, two elements in this quotient, in this subspace, you have two lines parallel to the given M. If you add them, then it corresponds to the addition of the two vectors that you picked up on this line. Therefore, corresponding to the sum of two vectors from this line, you have the corresponding sum in V by M. Similarly, you can say the same thing about the scalar multiplication. So you start with a vector in this case. Now let me write this N in N, and then you take a scalar multiple of that. Something like Cx. Cx also belongs to N. Then you draw the line parallel to N. Do that. That's the quotient generated by Cx. So that's exactly what we have. So you see that this is on its own a vector space. N is on its own a vector space because it's a line passing through. And we have carefully chosen that it is not identical with M, or it is not contained in M, I would say that way, or M is not contained in that. Okay, once you have that, now you see that every element of N generates a unique quotient. Okay, so there is the identification of elements in N with elements in V by N. Okay. Or what you say is that whatever be the dimension of N, as vector spaces they become alike. So the dimension of N is going to be the dimension of V by N. This is the intuitive feeling. Now we will see whether the same thing happens. So what is the status of n? The status of n is that n is a subspace of V with the property that m plus n equal to V. Okay, as we have shown here. Because this forms a basis, this forms a basis, and you see that the sum is equal to, or this spans these, the vectors here and the vectors here span the whole of R2. Okay, therefore what do we have? We have a credible speculation that the dimension of V by M is equal to the dimension of n, because every point, every element of n can be identified with an element in V by M, and corresponding to every element in V by M, there is some element in n which generates that particular element. That's the whole idea. In short, in the mathematical language, we would venture to say that there is an isomorphism between V by M and n. The status of n is that status of n along with M generates the whole space. And not only that, there is only one common point for M and n, these two subspaces, namely 0. Okay? Right? And such subspaces are called the complementary subspaces. For n is a complementary subspace and vice versa. But the unfortunate thing is that the choice of such an n is not unique, because you can choose any other line which is not lying in M, or M is not lying in that space. Okay, it also serves as this. Okay, for example, you choose this line. Choose a vector here, and then the line generated. This is some n prime. N prime also has a property that m plus n is equal to m plus n prime. Okay, it's equal to V. Only that you see that n prime is also a complementary subspace in the sense that the intersection of M and n prime consists of only the 0 vector, and every representation of a vector in V as a sum of a vector in M and a vector of n is unique. So also the representation of a vector as the sum of a vector in M and the sum of a vector in n prime is also unique. Okay, so n prime is another credible choice in place of n. Okay, so in fact you see that there are infinitely many lines that you can draw through the origin here, which is not identical with m. They all form what are called credible complementary subspaces. Okay, so what we observe is this. Okay. Right, I asked this question. What is that? What is the relation? What can you say about V by M? Is it sensible to expect it to depend on both M and N? What is the relation? This is what we are exploring. Okay, what is the dimension of N or N prime? the dimension of n or n prime, you see that is equal to n minus n. So here it is 2 minus 1, which is equal to 1. That's why you get 2 times. In the case of R3, suppose you were to start with a line through the origin as your m, then you see that a complementary subspace that you would have is a plane passing through the origin which does not contain the line. Okay? And every point in that plane generates a line parallel to the given line M. Okay? And if those vectors are linearly independent in that complementary subspace, then these two lines are also not identical. They are different. Okay. So in that case, you get a feeling that it's an R3. This is the picture, sort of picture that you have. You start with a line. You see that you can talk about all lines parallel to it. Now it is in the 3-dimensional space. There is all round parallel lines that you have. You should start with a subspace. So this is M. Space N such that R3. Then you see that through every point on this line, there is a line parallel. And you see that if you choose for every point on this, you have a unique line. They are all different. And one observes that some of these lines can be obtained from other lines. Some of them cannot be. In fact, you see that this is a 2-dimensional subspace. Therefore, you can prove that V by M dimension of V by M equal to 2, which is equal to 3 minus in the 3-dimensional. So that's a sort of picture that's emerging. So what we are going to do is we are going to like this. How to explore this? Now, first of all, you see that there could be many complementary subspaces. So we will try to get one of them. So we have to use the fact that V is n-dimensional and M is m-dimensional. Okay, thank you very much. Once again, wish you a very happy new year. Thank you.